In this chapter, we're looking at random variables. A random variable is a variable whose value is a numerical outcome of a random phenomenon being a probability experiment. Our notation for a random variable is going to be capital letters, such as capital X, capital Y, etc. An unknown value for a random variable is denoted by a lowercase letter. So if our random variable is capital X, then a value of capital X would be lowercase x, or x sub 1. So one of our favorite scenarios is flipping a coin. So suppose we flip a coin 3 times. Let's create the sample space for this scenario. Flipping a coin 3 times would result in 8 possible outcomes. Flipping a coin is a chance experiment, and the number of heads obtained is a variable whose value is a numerical outcome. So number of heads obtained is a random variable. It fulfills the requirements that it comes from a chance experiment and the outcome is a number. So let's call the number of heads capital X. Capital X is a discrete random variable because the outcomes for X are a fixed set of possible values with gaps in between. So the results of capital X would be 0 heads, 1 head, 2 heads, and 3 heads. It's not possible in this experiment to get 0.7 heads. It's not possible to get 2.3 heads. So therefore our variable is discrete. So here is a probability model of our possible outcomes. So we can make a probability model for things that are not chance experiments. Here, since this is based off of chance, the probability model is called a probability distribution. Notice that the number of heads next to it is x sub I. That's telling us that 0 heads would be x sub 1, 1 head would be x sub 2, 2 heads would be x sub 3, so on and so forth. Probability next to it is p sub I. That denotes the variable for probability. All the probabilities in the probability distribution denoted p sub I have to satisfy 2 conditions. These 2 conditions are the same that we've been working with when talking about probability models. Each probability must be between 0 and 1, and the sum of all the probabilities in the distribution must equal 1. Next, we can use our probability distribution to create a probability histogram. Our x-axis is going to be the value, which in this case is the number of heads obtained, and our y-axis is the probability of that event occurring. Because these variables are discrete, I'm going to align my bars such that the midpoint is going to be the value. Let's say we're finding the probability that our random variable is less than 1. So I go to my histogram, and the only bar here where the probability is less than 1 is the first one. So that is the probability of getting 0 heads. This corresponds to a probability of 0.125. Finding the probability of getting exactly 3 heads is possible because this is a discrete variable. The probability of that occurring is 0.125 again. Since this is not a density curve, we did not make an idealized curve to fit our data. This is a histogram of discrete variables. We can find the probability at an exact value. The probability of being greater than 2 is only one possibility, which would be getting 3 heads, 0.125. The probability of getting heads greater than or equal to 2 now includes our 2, so the bars for 2 and 3 should be shaded for a total of 0.5. So in a discrete random variable, there is a difference between greater than 2 and greater than or equal to 2. Because this variable is discrete, we can find the exact value at 2, which will make the probability larger than if you were just looking for greater than 2. So our other type of random variable is continuous. When we use the random number table or the graphing calculator to select a digit between 0 and 9, the result is a discrete random variable. The probability model assigns the probability 0.1 to each of our 10 outcomes, 0 to 9, because each number has a 1 out of 10 chance of occurring. So 1, it's a random chance experiment because the random number table and the graphing calculator generate these numbers randomly. And 2, it's discrete because our outcomes are all numbers, whole numbers, nothing in between. So again, the probability of getting one of these numbers between 0 and 9 is a 1 out of 10 chance, or 0.1. So let's say we want to choose a number at random between 0 and 1, allowing any number between 0 and 1 as an outcome. There are now an infinite number of possibilities of numbers between 0 and 1. So the same space is not a set of distinct numbers, but instead an interval of numbers. So we know that with random digits, the outcomes are equally likely, but we can't assign probabilities to each value of x because there are infinitely many possible values. Instead, we can use a density curve. This density curve represents the area between 0 and 1. So imagine we could choose any number between 0 and 1. It could be 0.1, it could be 0.111, it could be 0.99, it could be 0.999, it could be 0.45. So this is the reason we're looking at an interval instead of looking at a histogram of discrete variables. We know from our past experience that the area under this density curve is going to be 1. So the probability of finding greater than 0.4 means that we are finding 0.4 on our x-axis and shading everything to the right. To find the area of this, we know the height of this rectangle is 1, the base is 0.6, so the probability of getting 0.4, or getting larger than 0.4 is 0.6. Looking for the probability of 0.5 is not possible. Since this is a density curve, we cannot find the area under an exact point. Another way of thinking about it is that the probability of getting 0.5 is 1 out of an infinite possibilities of numbers. 1 divided by infinity is going to be 0. So before we had discrete variables, we could look at the value at an exact point because they were discrete and the histogram showed each bar for each value. Since this is continuous, we cannot select one specific point. Finding the probability of less than 0.12, I find 0.12 on my x-axis. I'm shading everything smaller than that. This time our height is still 1, but our base is 0.12. So the probability is 0.12. The probability of x less than or equal to 0.12 is the exact same thing. Again, since we cannot calculate the value at an exact location for density curves, the probability of less than or equal to 0.12 and less than 0.12 are the same. Because any density curve describes an assignment of probabilities, normal distributions are probability distributions. So for instance, the heights of young women closely follow the normal distribution with mean of 64 inches and standard deviation of 2.7 inches. Let's let capital Y represent a randomly selected woman. If we repeat the random choice many times, the distribution of values of Y is the same normal distribution that describes the heights of all young women. So let's find the probability that a randomly chosen young woman has a height between 68 and 70 inches. In the normal distribution with mean of 64 and standard deviation of 2.7 inches, we're finding the area between 68 inches and 70 inches, or the probability of 68 less than x less than 70. Remember, since it's continuous random variable, we could put equal to signs below the inequality signs. It means the same thing. So our normal distribution looks like this, with a mean of 64, standard deviation of 2.7, and I approximated where 68 inches was and 70 inches. We're looking for that area. So using my graphing calculator, or you can use your z-score table, I used normal CDF, where the lower bound was 68 inches, upper bound 70 inches, mean is 64 inches, and standard deviation is 2.7 inches. So in the calculator, the probability of a randomly selected woman being between 68 and 70 inches is 0.0561. So the probability that a randomly selected woman is between 68 and 70 inches tall is approximately 5.61%.